Now I start recording. So before guys we go over the problem solving for today. Uh, sorry. Okay. Quickly, I wanted to go over the theory of the air resistance lab. Air resistance, drag force, air resistance force, it's called drag force as well. It's not going to be covered in your final exam. But in case you had some questions when you went over the lab, I'm going to go over it quickly. Guys, before being familiar with air resistance, you considered an object. If you drop it, let's say you drop it, uh, it's going to drop under the influence of only the force of gravity. uh, Drop V0 equals to zero. The force is only gravity. And we use kinematics equation. Acceleration is going to be equal to G. Magnitude of acceleration is going to be equal to G. We use kinematics equation to find uh, velocity, position, time, and basically any other parameters needed. Or for example, we use dynamics. Sigma f equals to ma, and we use a equals to g. Now, in reality, what happens when you drop an object or throw it, let's say in one dimension, which was the topic of your lab, the moment you drop it, the only force is going to be equal to mg. At the drop is going to be the only force is going to be equal to mg. And then as the object gains some speed, air resistance increase. Air resistance, it depends on the speed. If the speed equals to zero, air resistance or FD, F drag force, D for drag force, is going to be equal to zero. So if you drop an object, the air resistance on it is going to, at the beginning only, is going to be equal to zero. At the drop, V0 equals to zero, air resistance is going to be equal to zero. And as the object gains speed, the air resistance increases. Uh, if the object uh, if the object gains a very high speed, air resistance will depend on FD will depend on this is proportionality is going to be proportional to V squared. That means if you double your speed, air resistance quadruples. If you triple your speed, the air resistance is going to be 3 to power 2, 9 times greater. The higher, you probably notice this, guys. When you run faster, you feel the air more. Uh, you feel the air resistance. It's a, it's a force that depends on speed. And in most cases, the speed is squared. In some cases, it's if the speed is slow, it depends on the speed itself, not v squared. Okay, so if we were to think about free body diagram, a teeny tiny time after, there is going to be mg. Mg doesn't change, of course, comes from planet Earth, and there is going to be teeny tiny fd. And as the object, let's say ground is here, as the object is moving down, air resistance increases. It's not constant. The higher the speed, the higher the air resistance. And at some point, I should have drawn with black. At some at some point, the air resistance would be equal to if this is mg, the magnitude of air resistance would be exactly equal to mg. This is at this point we call we say that the object reaches or reaching terminal speed. At this point, mg would be equal to f drag. Mg would be equal to a constant. In your lab, we called it B, a constant which depends on the material, which depends on the cross-section of the object. The more area, you see that, for example, skydivers, they do this. They want to increase the area and they want to increase their B, the value of B, when you do this. If you, instead of doing this, facing air this way, if you fall down feet first, your B is going to be very small. So yeah, that's why skydivers they would do this. They call it a spread eagle position. B multiplied by B squared. And this B squared is going to be equal to mg over B. And B would be equal to the square root of mg over B. That's the terminal speed. We show it by T. What's the significance of terminal speed? The moment the object reaches terminal speed, it's going to move with constant velocity down. mg and fd, they cancel each other out for the rest of the path. They're going to cancel each other out, and the object moves with constant terminal speed. That terminal speed, the smaller it is, the better, or the higher it is. Do you want, when you fall down, do you want high terminal speed or low terminal speed?
Low terminal speed.
What was Aaron?
I think a low terminal speed.
Low terminal speed. You want a smaller terminal speed, yeah. I think that's what you said, right? If you, the smaller, if you hit the ground with high speed, you're gonna break bone or you're gonna be dead, right? You want as small as terminal speed as possible. So to reach a low terminal speed, you need uh, a long distance from the surface of the Earth, so that you open up your parachute. If you are parachuting, you open up your parachute, and then giving the uh, giving the drag force time to be equal to mg, and then you reach a small terminal speed, and then go down. Okay. Um, so. That was a little bit about your lab. Um, in case you would like to hear a little bit about the theory of it, the rest of it is was learning to play around with Excel, which you guys, all of you, did well. And yeah, the theory is this. Now let's go over the problem solving for the last chapter. Let me open up the chapter. Uh, just give me a second to take to take the attendance. No. Okay. Now we're on the chapter 10. We're gonna solve some problems from chapter 10. Make sure the problems that we solved during the class last time, um, from the textbook, we went over some examples here. Make sure to go over them. Now let's go over the problems. Um, do you want to try 36, guys? Or it's too easy, too easy. You want to try something else? So have your calculators ready, and I want your curiosity. I want your questions to deepen our understanding for the questions. Let's go over it. The angular position of the rod varies as uh, 20 t squared. So uh, that 20 t squared is that 20 t squared is what, guys? Is equal to what? The angular position. It is which parameter? Exactly, Eric. It is, it is theta. Uh, so that is theta. Theta equals to 20.0 t squared. Radians from t equals to 0. The rod has two beads on it as shown in the following figure. One at 10 centimeters, the red bead, and the other one at 20 centimeters, the blue bead. What is the instantaneous angular velocity of the rod at t equals to 5 seconds? What should I do for angular velocity? It's best that you talk. If you don't want to talk, you can type. But uh, without your participation, I would assume that you are okay. The problem is way too easy. So I need your participation. No participation, we're gonna go, we're gonna say goodbye. Uh, yeah.
So we
Uh-huh.
differentiate.
Exactly. Exactly. Thank you, Anthony. Thank you, Marshdeep. Uh, thank you, Julian. Yeah, and Parmod. Thank you, guys. And Eric, of course. Omega equals to d theta over dt. So in this case, d of 20.0 t squared, which is going to give you 2 times 20 is going to give you 40.0 t. And then omega at t equals to 5 seconds is going to give you 40.0 multiplied by 5. Exactly. Just going to need 200. 200. Again, guys, you see 5 seconds is given to you with one significant figure. 40.0 has 3 significant figures, so we should have 2 significant figures here. What is overall the way that they dealt with significant figures are not great in Openstax textbook. But anyways, there are very good problems. The unit is exactly radians per second. Exactly. Um, that's part A. Part B. What is that's A. Part B. What is the angular acceleration of the rod? Then you need alpha. Alpha is the omega over dt, which is going to give you the dt of 40.0 t, which is 40.0. And the unit is going to be radians per second squared. It would be 40 Coulomb, yeah? Not 400, I believe, right? Yeah, yeah, yeah. Thank you. I'm double checking myself too. I may make uh, a calculation mistake, so no sorries. It's we are double checking the calculations. Part C. What are the tangential speed of the beads at t equals to 5 seconds? Tangential speed bt is going to be equal to b tangential. Let's call this beat 1. Let's call this beat 2. B tangential of beat 1 at, let me specify it. I'm going to call it red, and I'm going to call this the other one blue. That's not blue. B of red is going to be equal to R omega. Uh, R of red is going to be 10 centimeters. 10, converting it to meters is going to give you 0.10. And omega of red is going to be omega of red and omega of blue at t equals to 5 seconds are going to be exactly the same. And it was equal to 200. And B of blue is going to be equal to R omega. The radius of rotation of blue is 20 centimeters, 0.20, multiplied by, and it has two significant values, multiplied by 200. They move with exactly same angular speed. The radius are different. Yeah, so that's for part C. And part D, part D, to give myself a bit more space. Part D is asking what are the tangential acceleration? So tangential acceleration, what should I do, guys? Tangential acceleration. Part, what is it? D. A tangential is going to be equal to R alpha. For the red one, A tangential of the red is going to be equal to 10 centimeters. It's going to give you 0.10 meters. And alpha for both of them, we found that it's time independent and it's equal to 40. And A tangential of blue, the radius of rotation is 0.20 multiplied by 40. And you guys tell me last part E. What's going to be the centripetal acceleration? A centripetal of red is going to be equal to V squared over R, exactly. Yeah, yeah. Um, V squared. Is there any V centripetal in circular motion? Is there such thing? No. It's always V, the only V that you have is tangential, is tangent to the path. Path is circular, and the only velocity speed you have is tangential. So you're gonna do V squared over, or you don't need to label it tangential or centripetal because there is no V centripetal overall. V of red is this much. 0.10 times 200, which is going to give me 20. It's actually only 20 because 0.10 has two significant figures. 20 squared divided by the radius is 0.10. And a centripetal of blue blue, which is going to be this 40 divided by 1. And that's the centripetal acceleration of each of them. Make sense? The question is, what are the centripetal acceleration to be at 5 seconds? So, Harmod is asking why they say at 5 seconds. The reason is, you don't know. It could be time dependent. In this question, it wasn't time dependent. Alpha was not time dependent. But if, for example, you had, here we got alpha, uh, alpha was d over dt of 40.0 t, which just gave you 40.0. That's it. Radians per second squared. But let's say, alpha was equal to d over dt of 5t squared. Then alpha would be 10t, and it would depend on time. Yeah. So yeah, it wants to test you to see if you know that here if you got an alpha to be constant and it doesn't depend on time, it's time independent. It doesn't matter at which time then. It's constant. Yeah. Okay. Next question, guys. Which one do you want to solve? 54 or too easy? I gave you 54. 54 or 65, or you want to see 54? 59. Did I give you 59? The aircraft, I don't think that I gave you this. Let's focus on the one that was on the assignment, and if we had extra time, we will go over it. We'll go over it. Uh, yeah, okay. Let's do 54. A system of point particle is shown. Each particle has a mass of 0.3 kilograms, and they all lie in the same plane. What is the moment of inertia of the system about the given axis? Axis, this axis, which is going to be out of page, right? Yeah, the axis is going to be out of page or into page, doesn't really matter. It's an axis of rotation, and these uh, these particles uh, are in the XY plane that I'm drawing. They are in the XY plane. What is the definition of moment of inertia is? I is going to be equal to sigma mi ri squared, right? I equals to 1 to number of particles. How many particles do you have? 3. There are 3 particles, right? So m1 r1 squared plus m2 r2 squared plus m3 r3 squared. The question tells you that they have exactly the same masses. So m1, m2, and m3 are exactly the same. You can factor out m. R is what? Is the distance from,
Professor screen.
oh, you should have told me sooner, guys. Thanks, Harshpreet. Uh, yeah. So that's why, guys, I need you. I need you. Uh, if I record this on my own, and I do this, or the thing that I didn't show you the screen, I wouldn't notice. I need you here. I need your participation. I need you talking. I need you to ask me questions, both for uh, technical reasons, reason of recording, and also for deepen our understanding to make discussions, to talk more about the problem. So the XY plane, this is the XY plane that I drew. Moment of inertia, I wrote the definition of moment of inertia, sigma I equals to 1 to 3, mi ri squared equals to m1 r1 squared, m2 r2 squared, and m3 r3 squared. Masses were the same, you factor out mass. And yeah. Now, let's call this is particle 1, this is particle 2, this is particle 3. Particle 1, the distance that it has from the axis is going to be 0.60, right? I converted it to meters. Plus, second particle, this one, it has a distance of 0.40. And the third one, 0.20. That's moment of inertia about this axis. This
So
axis.
I
Yeah,
have a question.
yeah, go ahead.
Why is it that we aren't dividing by the summation of masses? Is that only for center of mass?
Yeah, that's the definition of center of mass. It's completely different. X center of mass, for example, is going to be sigma mi xi, not a squared, divided by sigma mi.
Oh, okay. Okay.
Yeah,
Thank you.
yeah, different definitions.
Okay.
Yeah. Okay, uh, that's part A of the problem. And part B of the problem is asking, what is the rotational kinetic energy? Kinetic energy is going to be rotational kinetic energy is going to be equal to half I omega squared. Is going to be half whatever you got from I, exactly per mode. Yeah. Whatever you got from I you're gonna put it into here, and omega squared, omega, they gave you revolution per second. Is that omega? No, that is revolution per second is a unit of
Force. No.
is unit of
Frequency.
frequency. Exactly. That's unit of frequency. And omega is going to be equal to 2 pi times frequency. So it's going to give you 2 pi multiplied by pi. So you're going to do 2 for the omega squared. Omega is going to be 2 pi multiplied by 5, 10 pi, and the whole thing is squared. That's going to give you the rotational kinetic energy. Make sense?
Yes.
Lucian, did I give you 59? If I gave you 59, we should solve it for the sake of your final exam. If not, no. Or at least it's not our priority. If we had time, we'd go back to it. Can someone tell me, did I give you 59 or no? No? Okay.
You did.
Okay. Now let's go for the next one. 60.
So could you go back to the board to the previous number? I just wanted to look at it.
Yeah.
Thank you. Yeah.
Yeah.
That's okay. Thank you.
Yeah. Anytime. Anything. Thank you. Okay. Next one. Next one. Which one is it, guys? 65. Let's go for
65.
60. Let's go for 65. So it says using parallel axis theorem, what is the moment of inertia of the rod of the mass m about the axis shaft? What is parallel axis theorem? It's very easy. It's very easy. It says if you know, for example, if this is how about this, guys? How about I bring the table of moment of inertia from the textbook, which you will see it in the exam over here. Okay. This is the table of moment of inertia that you're going to see in the exam. It's going to be in the in the equation sheet of the exam. It's given to you. Okay, moment of inertia of some objects. So let's say uh, you know moment of inertia of this. Okay, this is a rod, a thin rod about axis through the through center perpendicular to the length. I'm going to redraw the rod. Okay, this is going to be the rod. Where is the center of mass of it? It's going to be exactly at the center, right? Now, this axis, if the axis of rotation is passing through the center of mass, this is axis of rotation. Now, if you know moment of inertia about this axis, let's say you know it's going to be ml squared divided by 12. Let's say you know it. Then you can find out moment of inertia about any axis that is parallel to this. So, for example, if you want to rotate this about this axis, which is exactly parallel, I'm going to call this axis 1. And I'm going to call it axis 2. Moment of inertia about axis 2 is going to be equal to moment of inertia about axis 1. Here, axis 1 is going to be it's an axis that passes through the center of mass. I can call it an axis through the center of mass. I1 or I center of mass plus m, the distance between the two axes, the shortest distance between the two axes, d squared. I center of mass is going to be ml squared divided by 12. That's the first time, which is for this. Okay, the distance is how much? The distance is this much, the distance between the two axes. This is going to be d. It is here, in this case, it's going to be half the length of the rod plus m, half the length of the rod. If you call the length of the rod big L, I have to use big L. Half the length is squared. So let's see what I get. ml squared divided by 12 plus, I should have used big M. If I use big M, you should keep one notation. If you use a small m, use a small m all over. If you use big M all over. And L squared divided by 4, right? And if you add these two, the ml squared is going to be exactly the same in all, right? That's going to give you ml squared divided by 12. Sorry, divide by 3. Am I right? Three, yes, 3. ml squared divided by 3. Which is exactly here. Yeah, which is exactly this. This is parallel axis theorem. Let's apply it to this problem. So it says, using parallel axis theorem, what is the moment of inertia of the rod of mass m about the axis shown? This axis. I know if this is this is the center, so that's going to be L over 2. This is going to be L over 2. And there is an axis passing, this axis passing through the center of mass. This is the axis passing through the center of mass. If I want to find out, if I want to if I know the moment of inertia about the orange axis, I center of mass, which is going to be ml squared divided by 12. It's this guy. You can use this for this question as well, but one of them is equal. Okay. I center of mass is going to be ml squared divided by 12. Then I center of mass about this black axis is going to be about the black axis is going to be I center of mass plus m. The distance between them is squared. What is the distance between them? The distance between them is this much. I'm highlighting it in yellow. The distance between them, this yellow, is how much? Is L over 2 minus L over 6.
6.
Exactly. Which is going to give you 4L over 6, right? 2L over 3. Am I right, guys? No.
So I'm getting
Yeah,
3.
that's good. So it's going to be
2L over 6.
thank you, guys. So that's going to give me ml squared divided by 12 plus m L over 3 squared, which is going to give me ml squared divided by 12 plus ml squared divided by 9. That's going to be the moment of inertia of the rod about the axis shaft. Are we good? Let's take a look at more problems here. Go ahead, Lucian.
Kinda lost on how you got the L2, L out of 2 that you subtracted from with the L out of 6. Yeah.
That orange axis is going to be passing through the center of mass, right?
Yeah.
Yeah. If it passes through the center of mass, the center of mass of this thin rod is exactly at the center. It divides the rod into 2.
Yeah.
Yeah. So that's where the L over 2 come from. And L over 2 minus L over 6 is the distance between the two axes.
Oh, okay. Thank you.
Yeah.
Professor,
Yeah. Go ahead.
we have to use the diagram to find the ml squared out of 12.
Yes,
3.
yes. You need to know that. You need to know the parallel axis theorem only works if you know the moment of inertia of the system about the axis of rotation that passes through the center of mass. You need to know that from a table.
Does that mean also have to derive it? 'Cause, okay, the stuff you wrote in blue, is that also included?
The stuff I wrote in blue, that's
Yeah, do we have to derive it as well?
no, this was an example. I don't
Oh,
uh,
okay.
this was an example of parallel axis theorem. Using parallel axis theorem, to if you know this, you can get this from parallel axis theorem. That's what I was talking about in blue here. Okay. Now 67, right?
So, and this question, if you were setting a number like this, would you provide us with these formulas, the ones to the side, or would we have to know them?
This
Those,
table,
yes.
this table, I said, yeah, this is going to be in your equation sheet.
Oh,
If you look
okay.
at the equation sheet that they sent out, that's this table is there.
Okay.
Yeah.
Thank you.
Take a look at, guys, everyone, take a look at that equation sheet that they sent you out, that they sent out. It's, I think I did it in an announcement, right? It's in an announcement is, and also it's under one of the modules on one of the modules on Canvas. I think it's gonna be the first modules, first or second modules. But yeah, you can look at the equation sheet. This table is there.
Thank you.
Yeah. So 65 we did 67, right? Let's do 67. Slide the table in case we need to table here. There you go. Oh, a uniform rod of mass 1 kilogram and length of 2 meter is free to rotate about one end. If the rod is released from rest at an angle of 60 degrees with respect to the horizontal, what is the speed of the tip of the rod as it passes through the horizontal position? We want to find out the speed of the tip of it when it passes through the horizontal position. This V here is unknown. What should we do, guys? What have you done for this question? The axis of rotation is this guy. This is going to be the axis of rotation. It is the axis of rotation that is out of page. And rod is rotating about it. It's like this. The rod is rotating about it with respect to me, clockwise. Yeah. What should we do? How are you going to use moment of inertia? Your understanding of moment of inertia, your understanding of probably energy. How are you going to apply it here? Eric says mg1 equals to half pi omega squared. So Eric, you want to use conservation of energy, right? Which y are you going to use, right? Which y are you going to use? Like in your L over 2 sine 60. Why L over 2 sine 60? I'm asking this from Eric. Eric is saying y should be equal to L over 2 sine 60 degrees. Exactly, Eric. That's right. So Eric is saying, look at we have to look at the center of mass. Okay. If you want to write down conservation of energy for this rod, the mechanical, if there is no non-conservative forces, there is no friction, air resistance, anything that consumes mechanical energy. Mechanical energy is going to be conserved. Mechanical energy at this point, at this orientation, 1, until it comes to the point B when the rod is completely horizontal. So 1 is when the rod is at 60 degrees with horizontal, and 2 is when it's completely horizontal. Mechanical energy at point 1 is going to be equal to mechanical energy at point 2. Excuse me. Mechanical energy at point 1 here is going to be gravitational potential energy. Let's continue here. Back to space management. Or how about mechanical energy at point 1 is going to be equal to mechanical energy at point 2. Then for this, you have to take a look at the center of mass. The mechanical energy of the center of mass. That point represents the whole rod. If you want to write down for one point, that point should be the center of mass, which represents the whole rod. Okay, so that's going to give you gravitational potential energy. There is no spring, so there is no elastic potential energy plus kinetic energy. 1 equals to gravitational potential energy 2 plus kinetic energy 2. Okay, since we have gravitational potential energy, we have to set up our coordinate system. We have to set up our y-axis at least. Or that's only needed. The only coordinate when you have gravitational potential energy, the only coordinate system you need is going to be y-axis. Go ahead, Lucien.
From looking at the number, how did you tell that mechanical energy was conserved?
How can we say mechanical energy is conserved? That's Lucien's question. Anyone? Can anyone answer that question? Why mechanical energy is conserved? Work done by non-conservative forces. Yeah, exactly, Eric. Yeah. Work done by non-conservative forces is going to be equal to change in mechanical energy. If work done by non-conservative forces is 0, then change in mechanical energy is 0. Mechanical energy at point 1 equals to mechanical energy at point 2, mechanical energy at point 3, and so on and so on. Yeah, there is the only force here, Lucien, the only force here is going to be gravity, and gravity is not a non-conservative force. Gravity is a conservative force. So that's what. Okay. Now, guys, in this equation, what is 0? Barmot, I will get to your question. We're not there yet. What is 0 in this equation? Yeah, what's 0? Give me the zeros.
Kinetic energy of
energy.
first.
Kinetic energy at first is 0. Exactly. What else? There is one thing else that is one thing else that is 0.
Potential energy of second.
Exactly. Potential energy of the second. Exactly. So gravitational potential energy of one. Gravitational potential energy is going to be equal to mg multiplied by the height of the center of mass, right? What is the height of center of mass? No, that's your question, Parmod. You tell me, Parmod, yourself. This height is how much?
Half of the length.
This much is L over 2, right? This much is L over 2. And this angle is 60 degrees. This black line is going to give you L over 2. Let me be consistent with my L. Let's use the small L. L over 2 sine 60 degrees. So that's why. So mg multiplied by L over 2 sine 60 degrees is going to be equal to half. The kinetic energy is rotational kinetic energy, half I omega squared. And now what is omega? Let's take care of the right hand side of the equation. What is I? From the table, which one do you choose? I.
ml squared by cube. Oh, sorry, 3.
ml squared divided by 3,
3.
exactly. ml squared divided by 3. Okay, let's, I'm gonna come back to this. Harmod and Mohit. This didn't make sense? Half the length, because this is center of mass, it makes it L over 2, right? And then you want the height of the center of mass. Height of the center of mass is this black line, which is going to be L over 2 sine 60. Tell me what you think.
Professor, is it L over 2 sine 60 coming through the components? If
Can
we
you say it
take
again?
components of L by 2, or why it's L by 2 sine
I'm
60?
not looking at component of anything. I'm looking at the height of the center of mass. At what height is it with respect to this 0? If this is 0 on the y-axis, what is this height? I'm looking at that. And since this is the center of the rod, this distance is L over 2. And this black line, which what I'm looking for, is the opposite of angle 60. Yeah? Does it make sense or no? Can you help me?
Professor, I didn't get it. Like why it's L over 2 sine 60? Can you please elaborate it a little bit?
Okay, one more time. Uh, what are we looking at? You tell me. What are we looking at? What you want to find out what?
The height of center of mass?
The height of center of mass with respect to this zero, right?
Yeah.
Do you agree that it is this black line?
Yeah.
Yeah. Do you agree that
Yes,
this much
Professor.
is L over 2?
Yes, Professor.
Then this is going to be L over 2 sine 60. This angle is 60 degrees.
Okay.
Yeah, that's it. Just geometry. Okay, Parmod, do you agree as well? Yeah, okay, good, good, good. Okay, so now everyone, so hopefully everyone, we're all on the same page now. Everyone knows that why we chose ML squared over 3? Any objection of using that omega, that I? We're looking at the moment of inertia of about an axis that is a rod. You should look for a rod. So a rod, which is gonna be either this or this. The axis here is not passing through the center of mass, it's passing through one of the edge. And that's why we chose ML squared over 3. Okay, now
Can you repeat that, Professor?
okay, so it's a rod. This is a rod. The axis of rotation is this guy, right? Is this guy. That's a point on axis of rotation. It is perpendicular to the rod and passing through one end of it. A thin rod. So it's like this. This pen rotates about my index finger. My index finger is the axis of rotation and it rotates about it. So you're gonna choose this ML squared over 3. Omega squared. So it's small m g L over 2 sine 60 degrees. The m's are gonna cancel out. You plug in the numbers and you will get omega. The only unknown here is going to be omega. And once you found the omega, the speed of the tip is going to be V equals to R omega. And R is 2 meters, 2.0 meters multiplied by omega. You get omega from here. 3.58 R mode. That's the speed. Oh, that's the omega. R mode got 3.58. You can compare your answers with each other to see if it's right or not. But yeah, that's it. That's it. Any question, Chris? If there's any question, I'm gonna go take a break. Let's There is a pendulum consists of a rod, this rod, with a mass of 2 kilograms and length of 1 meter, with a solid sphere at the end. The mass of the solid sphere is 0.3 kilograms and its radius is 20 centimeters. If the pendulum is released from rest at an angle of 30 degrees, what is the angular velocity at the lowest point? Okay, guys, what should we do? Give me your strategies. Still waiting. Okay, Eric, you're gonna use the same strategy as before, right? MG, MG1, let me use cover. MGY equals to half I omega squared. Exactly same strategy as before. Then what are you gonna do for Y, for I? Y is gonna be what? I is gonna be what? This is
So Y
basically,
will
go ahead, Harsh.
half of length with the angle that it's making.
Okay, half of the length of the rod with the angle that it's making. Okay, you're gonna consider the height measured from here, right? Maybe. Okay, that's gonna be high. First of all, is mechanical energy is conserved? Is mechanical energy conserved, guys? Yeah, mechanical energy is conserved or no? There is no non-conservative force here. The only force acting here is gravity, and gravity is a conservative force. So mechanical energy at point 1 is going to be equal to mechanical energy at point 2 equal to point 3. But we have 2 points. 1 point, I'm going to call it this. This is going to be point 1, and this is going to be point 2. Point 1 is where the rod and the sphere at the end, the pendulum is at 30 degrees. The releasing point, point 2, is going to be the bottom. Okay. So, no, help me, guys. MGY, as Eric said, is going to be equal to half I omega squared. And now Harsh gave some thinking about the Y. What's going to be the height? The height of what should be considered? The height of the rod, the height of the sphere. The height of center of mass. Y is going to be the height of center of mass. What is the height of center of mass here? Where is center of mass? Where is the center of mass? And I want to find out its height, right? Where is it? Duncan is saying X center of mass using equation of center of mass M1 X1 plus M2 X2 divided by M1 plus M2. Okay. And how do I use that, Duncan, or anyone else? What's gonna be my M1? What's gonna be my M2? Okay, go ahead, Harsh.
No, sorry.
No, it's okay. Give me ideas, let's discuss it. Okay, so how do I proceed, guys, then? I want to find out the position of the center of mass. Position of the center of mass of a rod with length 1 meter and a sphere at the end with the radius of how much? 20 centimeters, mass of 0.3 kilograms. So Eric is saying 2 multiplied by 1 plus 0.3 multiplied by 1.1. 1.1. Okay. Divided by 2 plus 3. First of all, guys, let's make the x's let's make them y. Okay, let's make them y. Y center of mass is going to be equal to m1 y1 plus m2 y2 divided by m1 plus m2. Our task right now, we're going to get back to this. But we want to get back to this with the value of y, right? And value of y is the position of the center of mass when it's at the releasing point, right? Position of the center of mass. What's going to be the position of the center of mass? What's going to be the position? The question you should ask yourself, what's going to be the position of the center of mass of a rod with 1 meter length, mass of 2 kilograms, and that rod has a sphere attached to the bottom of it. Where's going to be the center of mass? Y center of mass is going to be m1 y1 plus m2 y2 divided by m1 plus m2. Let's consider the y-axis. Okay, so Eric is saying use this 2 by 1 plus 0.3 by 1.1 divided by 0.3, 2 plus 0.3. Two times 0.5. 0.1. Harshpreet is saying L over 2 minus L over 2 cos 30. Harshpreet, what does that? Why is that?
So L by 2 cos 30 is from the first sphere, and then
Yeah.
L by 2 comes to the second one when it's directly on the axis. So that is L by 2. And it's cos 30 because it's bottom, I guess.
Okay. And okay, so then let's go back to it. Let's go back to cos 30 later on. Let's find out first the position of center of mass. Eric, you consider you consider this would be your 0. Am I right? Okay. So Eric says, no, I can make sense of Eric's solution. But Eric, correct me if I'm wrong. Eric says you have two objects. One, the rod. The other one is the sphere. And that's why Duncan also suggested this M1 Y1 plus M2 Y2 divided by M1 plus M2. Okay, we want to find out the center of mass of this thing. This thing. The center of mass, if you had only the rod, the center of mass of the rod would be exactly at its center of the rod. So this is the length of the rod. You divide it by 2. The position of it is going to be at the center. So 0.5. Why 0.5? Because it's 1 meter. Oh, we're going to go over it, Agapi. Yeah. So that's going to be the mass of the rod is 2 kilograms. Mass of the rod is 2 kilograms. The center of mass of it with respect to this 0 that Eric considered is 0.5. Everyone is on board with this?
Yes.
Yeah.
Yes.
No. Perfect. Thank you, Anthony. No, let's go to our second object. Our second object is what? Is this a sphere, right? Is it a sphere or disk? Where is it? A sphere, yeah. It's a sphere. A sphere, where is the center of mass of the sphere? Surprise, surprise. That's at the center of the sphere, right? At the center of the sphere. Now, with respect to this 0, where is the position of the center of mass? From here to here is 1 meter. From here to here is going to be the radius of the sphere. Radius of the sphere is how much? 20 centimeters. So mass of the second object multiplied by 1.2. Exactly. Yeah, 1.2. Oh yeah, no worries, Eric. Yeah, 1.2 meters divided by the sum of the masses. So now you found the center of mass, the position of the center of mass when it's vertical. When it is vertical, you know the position of the center of mass. Go ahead, Lucian.
Um, I'm a bit confused about that M2 Y2. Like, why is it that you used the mass of only the sphere, but then the is it the length or the radius? I don't know. But like, why is it that you used 1.2?
Okay, so look at here, for example. Let's say you have one mass here, and this is going to be X, right? This is going to be M1, M2. This distance is 1 meter. This distance is, I don't know, 5 meters. What's going to be the center of mass? X center of mass is going to be M1. X1 plus M2. X2 divided by M1 plus M2, right? M1, whatever the mass of M1 is, you put it in. X1 is the distance from M1 to the point where you measure. It's 1 meter, right? The second one, M2 multiplied by what? You tell me, Lucian.
It would be 6, is it?
6, yeah. 6 divided by M1 plus M2.
So now,
You
My
have two
question.
objects. Yeah, you
Yeah.
have two objects. The center of mass of the rod is going to be at its center, right?
Yeah.
0.5. The center of mass of the sphere is at its center. What is the distance from this to here? Let me do it with green. What is this distance?
It's
It's
1.2.
1.2.
Yeah.
Eric, what's your question? I don't understand it. What do you mean by vector?
X is has a direction, right?
No. Here, you only duration is not an effect here. You only put down the distance to the zero on your coordinate. You consider zero to be here. You consider zero to be here, and you measure the distances of the center of masses of each to the reference. Yeah. Now, what do you guys get here for this? The calculation of White center of mass?
0.5913.
Thank you. Are we centimeters or meters? Meters. Most likely you're gonna have one significant figures, yeah. I will give you better significant figures in the exam. If I give you this question, it's gonna be more organized in terms of significant figures, my questions. Okay, so that's gonna be why the position of the center of mass is gonna be 0.59. Okay. Now, what is the height of center of mass at the highest point, at the releasing point? Let me make the picture less busy. This is the bond, and this is the sphere. Y center of mass is going to be equal to from, if this is 0, Y center of mass is going to be equal to M1 Y1 plus M2 Y2 divided by M1 plus M2. And this is going to give you point. Quickly, 2 times 1.5 plus 0.3 times 1.2 divided by 2 plus 0.3, which is going to give you 0.59 something meters. Okay, now we know that the position of the center of mass is going to be here. It's about 0.59 meters, roughly around here. That's going to be the center of mass. Now, what's going to be the height of center of mass at this position? Exactly. Exactly, Eric, that's totally right. If this is the center of mass, let me zoom in into the picture, the geometry of it. If this is this is 0.59, the height, the original height, if I'm going to consider 0 to be here, if I'm going to consider 0 to be here, the original height of it is this much. right? The original height of it is this much, and the final height of it is this much, right? So this height is how much? Is 0.59 cos 30 degrees, right? Let me highlight the triangle that I'm referring to. This and this are exactly the same. Yeah. And this is the path of the circular motion of the center of mass. These two highlights are exactly the same. And then, how about I looked at this triangle. To find out 0.59 cos 30. Make sense so far?
Can you repeat it, Professor?
I want to find out the height of the center of mass, right?
Yeah,
The height
Professor.
of the center of mass when it is at point of release, right?
Yeah.
The height of center of mass, if you want to find out the height of center of mass, the height of center of mass is this much. Right?
Yes, Professor.
Do you agree? This is the height of center of mass. This is going to be y1. I'm going to call it y1. And this much is going to be y2. Do you agree?
Yes, Professor.
First tell me, what is y2? Everyone,
Is it
not only Mohit. Give me y2. The height of center of mass, uh, at when it's completely vertical.
It's the
Half of
distance
the
plus
length?
the radius.
One by one, Harshpreet, and also was it Anthony? Anthony, first go ahead.
Oh no, it was
It was Aaron. Aaron, go ahead.
yeah. I was saying I think you had the radius of the sphere plus the y2.
No, y2 is from zero. It's from 0 to the position of center of mass.
Okay.
Yeah. Harsh, go ahead.
Half of the length?
Why half of the
It's
half of
on
length of
the
what?
axis. It's on the same axis as the center.
Mm-hmm.
So it will be half of the length.
Agape point 41, y point 41?
1 minus 0.59.
1 minus 0.59. 1 minus 0.59. Okay, so you're gonna have good point, Agapi. You know that from here to here is how much?
0.59?
0.59. 0.59. 0.59 meters. And then, do you know from here to here is how much?
1.
1, not only 1. 1 plus
0.4?
0.2.
0.2 or 0.4?
0.2.
0.2.
If it's from the bottom. If it's from the center, it's going to be 0.2. If it's from the bottom, it's going to be
Oh, it's 0.4.
0.4.
0.4. Yeah, 1 plus 1. It's up to you. If you want to consider from the center, you can draw this vertical line from the center. That's totally fine. I drew it from the bottom of the circle, so I have to make it 0.4. 1 plus 0.4. So 1 plus 0.4, I should take out how much out of it?
0.59.
Exactly. 0.15. That's going to be y2. Yeah, perfect. Perfect. So 1.4 minus 0.59. Agapi, you got 0.81 centimeters. No, let's go find out y1. Let's go find out y1. y1, we want to find out, guys, do you mind if I erase, or let me see if I can do something better. Just give me a second. Same time. So don't use that in case anyone had to. It's the same one. So, okay, now I want to find out y1. y1 is, again, I'm going to measure from this guy and the center of mass. How much is this? Everyone, how much is this if this is center of mass? Everyone, how much is this if that's the center of mass? The red point that I drew is center of mass. What is the length of that red line?
0.5.
0.59. 0.59. We found from the position, from the center of mass, if this is hung vertically, the center of mass is going to be, this much is going to be 0.59. So position of center of mass is going to be from here to here is going to be 0.59. Is that the height of it? No, the height of it is this much. y1. Ask me questions if it doesn't make sense. Don't let me pass without without understanding this crystal clear.
So I have a question.
Mhm.
Why are we finding uh, why are we looking for the center of mass
Center of
for
mass.
these two positions?
Why are we looking at center of mass? Can someone answer Anthony's question? Why? Why are we looking at center of mass?
We are looking for MGY.
Okay. If you're not looking at center of mass, what should you look at? If you're not looking at center of mass, guys, you have to look at every single bit of particle on this system. Center of mass is a point that represents the motion of the whole system. If you can identify the center of mass, and follow the position of the center of mass, it can show you, it can like, let me give you a even more interesting example. Imagine, guys, a person is diving, right? This is water. This is water. The person is gonna jump and then hits the water. Jump in the air and hits the water. And the person is gonna go, let's say the person is gonna be an Olympic athlete, and the person is gonna go make several rotations while it's in the air. The motion is very complicated with those rotations. Let's say she makes several rotations. What is the simplest way to study its motion? Can you say the person is in projectile motion? Can you?
Yes.
Yes. Yes, the person is in projectile motion. The only point on the person that you can follow it clearly, and if you take pictures of that person frame by frame, if you take a video, if you identify the center of mass of the person, the center of mass of the person follows exactly a parabola. It's the position of the center of mass. That's the significance of the center of mass. It makes your life way easier. You have a very complex system like a person's body. A person's body. Look at the center of mass of it. The center of mass of it, in this case, in a very complicated motion like an athlete in Olympic diving, this position of the center of mass is going to be a pebble. No, going back to this problem, you have a rod and a sphere. You have the option of to study each particle of the rod and the sphere separately, or look at the center of mass. The center of mass of it works like a point. It's like a mass here goes from this height to this height. That's it. That's why we're looking at center of mass. It makes our life way easier.
Okay.
Very good
So,
question, Anthony.
yes.
Very good question.
Thank you very much.
Yeah. Always, guys, don't be afraid to ask fundamental questions. Most of the time, guys, sometimes some questions comes to our mind, and we think, oh, this question may be way too simple. Maybe let's not ask it. Maybe it's me, but yeah, most of our discoveries or new understanding comes from these simple questions. Why the hell are we looking at the center of mass? Okay, that was a good one. Okay, going back to the problem. Where were we? No, we found the height of the center of mass when it is completely vertical, but no, we want to find the height of center of mass when the pendulum is hung at 30 degrees and you release the whole thing. What is that Y1? We need help. What is that Y1? What should I do? Go ahead.
30 degrees is
Uh-huh.
I don't know how they call the angle. I don't know if it's is it alternating or something? But like the 30 degrees there at the top is 30 degrees as well here where there is the center of mass. So
Ah,
you would have um our 0.8, is it 0.81 meters from the center of mass to the lowest point, and then we would have cos 30 times 0.81.
You're very close. You're very close. You are super close. So what Lucian is saying, he is looking at this height. He is looking at this height. It's how much? This whole height. It's 1.4, right?
0.4. Yeah.
1.4. Exactly. And he says, let's take out this much out of it. Let's take out this much out of it. How much is that? How much is this yellow length?
0.59 cos 30.
Exactly, Anthony. Exactly. That's this is 0.59 cosine of 30 degrees. So then can I write down y1 equals to 1.4 minus 0.59 cos 30 degrees? Yeah? Can I do that?
Yes.
Yeah. Mohit, can I do that?
Yes, I guess, Professor.
Yes, sorry, can you repeat?
I think so, Professor.
You should be sure. Are you sure I can do
Uh,
that?
Not so sure, Professor. I'm just confused a bit.
Okay. Do you agree that this blue one, is 1.4?
Yes, Professor.
Okay. And do you agree that this is from here to here is 0.59?
Yeah, Professor.
Okay. Then look at this triangle. This is adjacent to angle 30. You have a triangle like this. This is 0.59, 30 degrees. This is going to
Uh,
be 0.59 cos 30.
yes, Professor.
Yeah, that's it. And the y1 is going to be 1.4 minus 0.59 cos 30. No, that's it. The problem is now it's solved. You have, where did I write the conservation of mechanical energy? Conservation of mechanical energy. Let's, let me start from here. Mechanical energy 1 is going to be kinetic energy 1 plus potential energy 1 equals to kinetic energy 2 plus potential energy 2. Kinetic energy 1, 1 is going to be, 1 is going to be this is going to be 1, and 2 is going to be when it's completely vertical. What is 0 in my equation?
Kinetic energy 1
Kinetic energy 1 is 0. Yeah, exactly. Kinetic energy 1 is 0 because it's released from rest.
and potential energy 2.
Probably not. Because we found the y2, right?
Yeah. Okay.
Yeah. So let's write it down. So that's gonna give you mgy1, and whatever that we write is for center of mass. It's gonna be kinetic energy 2 is half I omega squared plus mgy2, right? So that's gonna give me mg y1 is gonna be this. You can just write down 0.81, or you can write down 1.4 minus 0.59. The reason that I'm writing down 1.4 because you're gonna see that 1.4 is gonna cancel out. That's it. Whatever that you consider as your chord as the origin of the height, it doesn't matter. It is gonna cancel out. Minus 0.59, which is gonna give you 0.81 equals to half I omega squared plus mg. Y2 is gonna be 1.4 minus 0.59 cosine of 30 degrees. Okay, now everything is done except for I. What are we gonna do for I? So you have I is gonna be I of the rod plus I of the sphere. I of the rod is gonna be a rod rotating about an axis that passes through the edge. Which equation should I use? You tell me.
It'd be ml squared over 3.
Exactly, ml squared over 3. A rod rotating about an axis that passes through one edge of it. If you could also use this and you would say, this is passing through the center plus, and since that's going to be on the edge, plus m, the distance between the two axes is squared. But this is given to you, so no need for it. That's going to give you I equals to, I used a small m for the mass of the rod, length of the rod, mass of rod, m. Let's use, did I use a small m? I didn't use any symbol for it. So ml squared.
I have a question.
Go ahead.
What is I?
Moment of inertia.
Moment of inertia.
Yeah.
Okay. Thank
Yeah.
you.
Yeah. Moment of inertia of the whole system. The whole system is going to be what you have. You have two objects. If you have three objects, you have to add up moment of inertia of all three of them. But yeah, you have two moment of inertia of rod plus moment of inertia of the sphere.
Thank you.
That's moment of inertia of the rod, yeah. And no moment of inertia of the sphere. Look at the picture and tell me if you have something from the table that can help you. I sphere, Eric is saying I sphere is gonna be, and also Don Kuhn, they're saying the same thing. They were saying I sphere plus IR. I of a solid sphere about center of mass plus m d squared. Duncan and Eric, either of you, why did you say that? Why did you say that? I of solid sphere about the center of mass plus md squared.
Oh, the first one is the ICM, and because ICM is 2m r squared over 5, and md squared is equal to m times, because the difference between the center of mass of the sphere and the axis is 1.2, so md squared is m times 1.2 squared.
Exactly. Exactly. First of all, guys, you're gonna take a look at a solid sphere. Where is in the table you have a solid sphere? This is here. What is the difference between this solid sphere and this one? These two pictures. Why didn't you use why should we use this? Why not this? What's the difference? They seem to be a sphere, right? Why? Which one should you choose? Anyone? Go ahead. Why left one? Why not the right one? Your voice is very low. Can you talk louder a bit? I cannot hear. What's the difference? The two between the two, what's the difference? Read them. What's the difference? That's a shell. The right picture is for a shell. A hollow sphere. Shell is a hollow sphere, like a soccer ball, for example. Inside of it is hollow. Inside of it is air. A solid sphere is like yeah, exactly, Guradeep. The pendulum is attached to this. The question says a solid sphere. The solid sphere is inside of it is ball, like the balls that you use for the projectile motion. Those steel balls. The inside of them is steel. Inside of them is not empty. But a soccer ball, inside of it is hollow. You go for solid sphere. 2 over 5 mr squared. Are we gonna use this only? No, as Eric and Donghoon said, uh, you have to add them up to the distance between the two axes. This is if there is a solid sphere, and this is going to be the axis of rotation. I is going to be equal to moment of inertia is going to be equal to 2 over 5 mr squared. But if the axis is here, if the axis is here, you have to add up the distance between the two axes. This is this axis is passing through the center of mass, you can use a parallel axis theorem in the previous problem that we went over. It was a previous one or two previous one. The distance between the two axes. The distance between the two axes is, I'm gonna write the m rod, L squared, length of rod divided by 3, plus 2/5 mass of the sphere, radius of the sphere squared, plus mass of the sphere multiplied. What is the distance between the two axes? Between the two axes is going to be 1.2 squared. This is this axis. This much is the length of, let me use this. From here to here is the length of the rod, which is going to be 1.0 or 1 meter. From here to here is from here to here is 1 meter, and from here to here is 0.2 meters. So that's what you're gonna do. Make sense, guys? Does the calculation of I make sense? Okay, yeah. Any question? Any question here on this? If that makes sense, then you're gonna put I into this equation, and the only unknown, everything is known. The only unknown is gonna be omega. Omega is going to be unknown, and you will be able to find out the angular velocity at the lowest point. Just remember, these two masses are going to be the total mass. The total mass of the system, which is going to be 1.3 kilograms. And then, yeah, the masses here, mass of the rod here is going to be 2 kilogram. Mass of the sphere is going to be, these two is going to be 0.3 kilograms. Okay, waiting for any question you might have. And one more thing, guys, you know that mg times 1.4, mg times 1.4 from the other side, both sides are going to cancel out, but you have to multiply mg by these two. They're not going to cancel out. Lucian, go ahead.
I wanted to ask about the in this calculation for the conserved mechanical energy, the m is which one exactly? Which mass is that?
Okay, this is mass of the whole system, which is 2.3 kilograms. And in I, the masses are clear.
Thank you.
Next question. Next one is going to be 69, right?
So could you go back to the previous number for a bit? Thank you. Got it, yes. You could go back to the number you're going to do now.
Okay. Now, another solid sphere question. A solid sphere of radius 10 centimeters is allowed to rotate freely about an axis. The sphere is given a sharp blow so that its center of mass starts from the position shown in the figure with a speed of 15 centimeters per second. What is the maximum angle that the diameter makes with the vertical? It's kind of the previous question without the rod, and you do the opposite. No, position one would have is completely vertical. It has only kinetic energy, and position two, it has some gravitational potential energy. Can we say mechanical energy is conserved, guys? Can we say that? Is mechanical energy conserved?
Yes.
Yeah, mechanical energy is conserved. Yeah, there is the only force is force of gravity. Work done by non-conservative force is going to be equal to change in mechanical energy. Here, work done by non-conservative force is going to be equal to zero because the only force affecting is going to be the force of gravity. Then we need to find out the position of the center of mass. Where is the center of mass, guys? Center of mass of a sphere is the center, right? Original height of the center of mass is this. That's going to be y1. And then you need to find out the final height of the center of mass, y2. So you're going to have mgy1 plus half mv squared. The kinetic energy here is given an initial velocity of 15 meters per second. Kinetic kinetic energy 1 plus potential energy 1 equals to kinetic energy 2 plus potential energy 2. Kinetic energy 1 is half mv squared. That's given to the center of mass. Plus mgy1 equals to kinetic energy 2. What's going to be kinetic energy 2, guys? Kinetic energy 2. What is it? Zero, exactly. Exactly, Eric. Kinetic energy 2 is zero. It says up to what point, up to what height it's going to go up. At the highest point, it's going to stop. So kinetic energy 2 is going to be equal to zero. Right? And potential energy 2 is going to be equal to mg y2. Okay. Now, do I use the moment of inertia here? Before doing that, tell me what is y1? What is y1, guys?
Centimeters.
Yeah, 10 centimeters, exactly. Y1 is going to be 10 centimeters. Now, what is y2 in terms of the angle theta? This was the center of mass. This was the center of mass. It goes up to this much. What is this difference? Is y2. Anyone? What is y2? This is y2. What is it? 20 minus 10 cos theta. Why? Why then 20 minus cos 10 cos theta?
Oh, because the diameter is 20 and the difference between the diameter and y2 is 10 cosine theta.
Okay. So what Eric is doing, Eric, correct me if I'm wrong. Eric is saying from, let me do it with orange. Eric is saying from here to here is going to be 2 times the diameter, right? And he's going to take out, let me do it with another color. Let me do it with green. He's going to take out this much out of it, which is going to be this green one is r cos theta, because this angle is theta, right? Then 2r minus 2r minus r cos theta would be y2. Is that what you're saying, Eric? Yes. Yeah. Do you agree with Eric? Any disagreement?
No.
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 Yeah, that's totally correct. Totally correct. Yeah, totally correct. This y2 is again it's geometry. Y2 is 2r, this whole thing, 2r minus this much, which is going to be r cos theta. So y2 would give you y2 would give you 2 times r is going to give you 20
Professor,
centimeters.
can you explain this again?
Sorry. When I'm done talking, don't interrupt me and I will go over it. Yeah. One person talking at a time. Otherwise, it's not going to work out. Cos theta. What do you want, Mohit?
Professor, the 2r minus r cos theta thing. So why it's 2r
Which part of
minus,
it? Which part of it? Which part of it?
uh, like I'm not, uh, I'm confused about the y2, like why it's equal to this one. Because,
Did you understand where the 2r come from?
yeah,
Okay. And do you understand? Do you understand that this is going to be y2?
yeah,
This is what we're looking for, right?
yeah,
If you if you find out this much, take it out of 2r, it will give you y2, right?
yes,
Yeah. And this much is going to be r cos theta. From here to here is r.
yes,
This,
Professor.
yeah, yeah. And then
Yeah,
this angle is theta. The green one is r cos
yeah.
theta. You take it out of 2r, that's going to give you
No,
y2.
yeah, yes, Professor. Now it's clear. Thank you.
Yeah, yeah, yeah. Okay. And remember, guys, do we know theta? No, we want to find out theta. Okay. Then, no, in our equation, we know y1, we know y2, we know the masses, okay? Should I keep this as half mv squared? Or should I do something else? Okay, give me ideas. Should I do it? Duncan is saying make it half I
I omega square.
omega squared. Aha, okay. Why?
V is equals to omega r. We have radius and we have V as well. We can find omega.
Aha, exactly. 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 V is going to be equal to R omega. V is 15 centimeters. Because it's centimeters, I'm going to make it 10 to the power negative 2. Don't forget about that. It's going to be equal to R. R is, what's the radius? 10 to the power negative 2. In here, it doesn't make any difference. Omega. And then omega is going to be equal to 15 divided by 10, which is going to give you 1.5 radians per second. Yeah, and that's going to be omega. And why? My question was, why between these two, which one do you choose? Half mv squared or half I omega squared to be in your equation? Why? Why I cannot use half or yeah, discuss which one do you which one are you gonna pick? Half mv squared or half I omega squared? Because it's very tempting when you see it's V is given to you and say, oh, kinetic energy is going to be half mv squared.
I think it's
Go.
because it's not moving in a direction that is v equal to 15 centimeters, whereas it's rotating with the axis. So it's not the velocity is actually not 15. It's with respect to the axis, it's another velocity, I think.
Okay. Kind of, just guys, let me post the store. Mowing grass in our neighborhood, and it's pretty low. At least for me, it's pretty low. Okay, so what is Eric kind of saying is that V is that is given to you. Uh, it if you look at the question, it says the center of mass has this speed. That's the speed of the center of mass. And half mv squared is going to be the kinetic energy of the center of mass. But what you're dealing with is a sphere, and there is a rotation, and it rotates the whole thing. It's rotating about an axis. If you want to find out the kinetic energy of the whole system, the whole sphere, the whole solid sphere, you have to uh, go with rotational kinetic energy, not only the linear kinetic energy uh, of the center of mass. You gotta go with the rotational kinetic energy of the whole system. The whole system is rotating. Every particle of the system has different velocity. The center of mass has 15 meters per second. Every particle would be different with respect to that axis. If you want to take into account all of that kinetic energy, you have to do sigma mi vi squared. If you do sigma mi vi squared for any particle, it's gonna give you half I omega squared. That's how the rotational kinetic energy saves you lots of complicated computation. So you're going to do half I omega squared plus mgy1.10 equals to mgy2.20. I converted to meters. 0.20 minus 0.10 cos theta. And this is going to give me half. What's I? What is I, guys? Moment of inertia of the sphere. Which equation in the table is the most? Which one is solid sphere? Only this, right? Are you going to use half two over 5 mr squared? Are you going to use this? Tell me what I should use for I. Aha, the solid, no, the axis, this is for an axis that passes through the center. If the axis of rotation was this blue one, then 2 over 5 mr squared. But since the axis is this one, you need to plus m times distance squared. So about this this is going to be about center of mass, and about this axis it's going to be I equals to I center of mass plus mass times the distance from these two axes is going to be R. So got a bit messy here. Let me see what I can do to make it a little bit more. at least easier to understand. This omega, let me do some color highlighting, so maybe that would help. This omega, the reason that we calculated it was for this guy. Y1, let's use this color. Y1 was for this guy. Y2 for this guy. And let's use purple. This I, we used it to find out this I. Yeah. Sorry, it got a bit messy, guys. But hopefully we'll get it. This is going to be I center of mass 2/5 mass times radius squared plus mass times the distance between the two axes, which is going to be this much, m r squared plus mg 0.10 equals to mg 0.20 minus 0.10 cos theta. Sorry, the omega squared is missing here. That's going to give me 1.5 squared plus. The masses here, they're going to cancel out. It's not like the previous example when we had two different masses. And then radius is given. The only unknown here is going to be theta. Am I right? Yes, the only unknown, I think I'm right. The only unknown here is going to be theta, and we'll be able to find it. Make sense, guys? Go ahead.
This class should have.
I wanted to know if you could like help explain that bit for the inertia again, like how you derived what to place inside.
So you have a sphere that rotate, that's going to be the axis of rotation, right?
Yeah.
That's what the problem is asking. From the table, we know that if the axis of rotation is perpendicular to the page, it's out of page, for example, and it passes through the center, that's going to be equal to what? 2/5. The moment of inertia is going to be 2/5 mr squared, right?
Yeah.
Now, every time you know the moment of inertia about an axis that passes through the system, that passes through the center of mass of the system, to here your sphere. If there is another axis that is parallel to it, these two axes, these two are parallel. These two are parallel. Then this is I center of mass. Since this is parallel, you can use parallel axis theorem. Parallel axis theorem is easy. It says I center of mass plus the distance between the two axes. What is the distance between the two axes? Radius of the circle, right? In this picture, radius of the circle. So yeah. That's how you get the I.
Okay.
Yeah.
A bit, it's still a bit confusing. Like,
Do you know parallel axis theorem?
not really.
We went over it. If this is the center of mass, okay, this is a rod, okay? If this is the axis of rotation, right?
Yes. Yeah.
Yeah. If you know this, let's say I center of mass for a rod a thin rod, about center is going to be ml squared over 12. You get this from a table, right?
Yeah.
Yeah. Then
Yeah.
Parallel axis theorem says, as long as you know the moment of inertia about that axis, the rotation about any other axis that is parallel to that axis, you can rely on me to find it out. Rely on parallel axis theorem. This axis, the orange one, the moment of inertia about that axis is going to be I center of mass plus the distance between the two axes.
Yes.
Yeah. That's parallel axis theorem. No, for the sphere, going back to the sphere, you know that this is from a table. The moment of inertia that about an axis that passes through the center. 2 over
Yeah.
5 mr squared, right?
Yes.
No, the question gives you an axis that is this axis that is parallel to that axis that is passing through the center of mass. Yeah?
Yeah.
Yeah? These two axes are parallel. This one and this one are parallel. They're both out of page. They're both out of page.
Could you identify those axes on the diagrams that were given?
They're out of page. They're out of page.
What I'm saying is like the way you've like indicated them down here, like can you identify them from the diagrams which were given up here on the question?
On the question, this is this axis.
Yeah.
That's it.
Then what of this second one? Because I'm trying to
This is from the
understand
table.
how
This is from the table. This is from the table. This is the question.
okay.
Yeah.
All right.
Make sense?
Yeah.
Yeah. Okay. So guys, any other question?
And the value of R is same, Professor.
Can I say it again?
And the value of R at the right
R is
side.
the radius. Yeah, it's the same. The distance between the two axes is turns out to be exactly the radius of the circle. Yeah, the values of the R are exactly the same. Yeah.
Can you tell me at the right side what we write here? 1 by 2, 2 by 5. We cancel M and the only value of left is R square.
Can you say it again one more time, Parmod? What?
And you identify all the values here. 1 by 2 into 2 by 5. You cancel all M here. And the only value left here is R square.
R squared, you know it, is 0.10.
Both R square are 0.10?
Yeah.
Okay, thank you.
Yeah. They are 0.10. So what Parmod is asking, these are R squared. They're both 0.10. 0.10. So that's going to be half 2 over 5 R squared plus R squared is going to give you 7 over 5 R squared 0.10 squared times 1.5 squared, and then the rest of the equation. Okay, so guys, I'm gonna go for my second break. Let's calculate the moment of inertia by direct integration of a thin rod of mass m, length l, about an axis through the rod as shown below. Check your understanding with parallel axis theorem. Let's go about the parallel axis theorem, okay? how can you use it, guys? Someone tell me, how do you use parallel axis theorem to find out the moment of inertia about this axis?
Is it ICM plus MD squared?
Okay, what is CM, Eric? What is center of mass?
Center of mass is L over 2.
Exactly at the center. The the axis that passes through the center of mass, that's gonna be the axis that passes. This is center of mass. It's you know that from here to this axis is gonna be L over 2, and from here to this end is gonna be L over 2. So I about this axis is gonna be equal to I center of mass, which is this axis, an axis that passes through the center of mass, plus m d squared. The distance, what is d? The distance between the two axes. D is this. Okay. I passing through the center of mass. What is it? A rod. Where are you? Here. Let's take this. Okay. A rod rotating about an axis that passes through the center of mass, which is going to be equal to what?
ML squared over 12.
Exactly, ml squared over 12 plus m. What is the distance between the two axes?
L over 2 minus L over 3.
And over 3.
Exactly. It's going to be L over 2 minus L over 3 squared. This distance, is going to be L over 2 minus L over 3. Right? And that's it. Sorry, I have to make the same M. So that's going to give you ml squared divided by 12 plus m L over 2. That's going to give you L over 6, right? It's going to be ml squared divided by 12 plus m L squared divided by 36. Am I right, guys? Yeah. Everything's right? Did you understand the procedure? Yeah, questions? No, further simplify this, there's going to be 3 plus 1, 4 ml squared. That's going to give me ml squared over 9, right? I don't ask you to find moment of inertia by direct integration. If you were interested, I can you can ask me and I can go over it. Or let me quickly go over it. Direct integration. It's not going to be in the exam. It's not going to be in the exam. This is going to be the axis of rotation. This is going to be L over 3. And this much is going to be 2L over 3. Okay, I will make this to be my x-axis, this to be 0 on my x-axis, the position of position of that point on the axis of rotation. Then I will divide this rod into super small, infinitesimally small DMs, with this, each DM has a distance of x toward the origin. From direct integration is going to be r squared dm. The distance of each of those dm is x squared dm. And the length of each dm, that's going to be x squared. The length of each dm is going to be, I'm going to call this dx. It's because it's on the x-axis. dm, I can write down dm is going to be equal to the total mass divided by total length multiplied by dx. So mass divided by L dx. That's going to be each dm. The mass of each dm is, you can show it by this. That's going to give, then it's going to give you m over L integration of x squared dx. My x's are going to change from here to here. If this is 0, the lower limit of the integration is going to be negative L over 3. The upper limit is going to be 2L over 3. That's going to give me m over L. Integration of x squared dx is going to give me x 3 divided by 3. From what to what? From negative L over 3 to 2L over 3. Then this is going to give me m over L, m over 3L, 2L over 3 cube minus negative L over 3 cube. M over 3L. This 2 cube 8L cube divided by 27 minus negative L to power 3 is going to give me negative L cube. Negative L cube divided by 27. So that's going to give me m over L, 3L. This negative with this negative cancels out, so that's going to give me negative 9L cube divided by 27. Then this is going to give me this L cube, but this is going to give me L2 and L2, and 9 over 3, that's going to give me 9, yeah. So exactly the same results by direct integration. I'm not going to ask you this. I'm not going to ask you this in the final exam, but it's good to be, it's good to know how this is derived, especially if you're gonna take physics 142 later on. It's good to know how to take these types of integrations. But mostly what I will ask, I expect you to know how to apply parallel access theorem, which we have practiced through the last 3-4 examples. Moving on to the last problem.
So sorry, could you just go back to the previous question for a bit? Yes. Thank you. That's enough.
Oh, that's it? Okay.
Yes. Thank you.
Yeah, no worries. Guys, any other question on this? What? What hanging mass must be placed on the cord to keep the pulley from rotating? See the figure below. The mass on the frictionless plane is 5 kilograms, so no friction. Frictionless plane, 5 kilograms. The mass on the plane that is connected to the cord is not, no, on the cord. The mass on the plane, I misread it. The mass on the plane is connected to a cord that wraps around the pulleys in a radius of 20 centimeters. Oh, okay. So this is connected to the pulleys inner radius. The inner radius of the pulley is 20. Guys, the pulleys that you saw in the lab, they have just one radius, right? It had one radius. There are pulleys that can have two radii. This plural of radius is radii. This is one of those. It has two radius. One is connected, the one on the plane, on an inclined plane, is connected to the smaller radius of it, and then uh, the design of the pulley is so that this string is going to wrap around it. It makes a complete, or maybe one round or maybe two rounds. It doesn't, it depends on the pulley, and then it goes to the upper radius. That's what is happening inside with for the string. So it's gonna go this way. Now, the hanging mass is connected to a cord that wraps around the pulley's outer radius. What we want to find is this M. What should we do? What should we do? Give me ideas, strategies. What do you think? We're gonna use torque. Can you, Duncan, can you tell us what are you gonna use? Yeah, torque. Good point. Okay. Torque of what equal to what? Torque left equal to torque right. Okay. Y equal, Duncan. Y equal. Exactly, you're right. You're right. To keep the pulley from rotating. That means no rotation. No rotation, that means sigma tau should be equal to 0. Sigma tau of the pulley should be equal to 0. Rotation, there shouldn't be any tau. If there is tau, it's going to rotate. Now, okay, torque. No, we're going to take a look at the torques on what? Torques of the pulley, torques. What is rotate? What can rotate here? The pulley, right? Torques on the pulley equal to 0. Sum of torques on the pulley should be equal to 0. Now, then, yeah, help me with the next line. What should I do next? What is connected to the pulley? What forces are acting on the pulley? Exactly, Dankun. There are tensions. How many tensions, Dankun? Two tensions, yeah, Hormone, that's right, two tensions. One is from this side, that's this tension, and the other one, and if I consider, let me use red. If this is the center of the pulley, this distance is 20 centimeters, and the other tension is applied here. That's the other tension. And this distance is 30 centimeters. These two tensions, the torque of these two tensions have to be exactly the same, right? This tension equals to what? Let me call this tension on the left, tension on the left, tension on the right. Tension on the left equals to what? It's going to be exactly the tension on this mass, right? That's going to be T. And this T has to be equal to what? Exactly, that tension has to be equal to the component of gravity. If this is mg, this is mg sine 30 degrees, right? That's and this is gonna be mg, sorry, not that. That's gonna be normal force, and this is gonna be mg cosine of 30 degrees, and there is normal force. Okay, normal force is going to be equal to mg cos theta, but we don't need it, right? We don't need it. What we need here is we know these two are enough. These two are enough. Mg sine theta and Tl. Guys, if the pulley doesn't rotate, the whole system is at equilibrium, right? Mass 5 kilograms is not going to move. If it doesn't move, that will tell you Tl is going to be equal to mg sine of 30 degrees. Right? mg sine of 30 degrees. So this TL is going to be mg sine of 30 degrees. So far, are we good? Are we good so far? Any question? Yeah, are we good? No. Next, what's gonna be TR? TR is gonna be equal to big MG. Close the window. Again, the mowers. I believe Zoom cancels out all the noise. You don't hear it, but I hear it, and it's pretty annoying. So if I do this, sorry, just the only thing I wanted to say here, this M is 5.0 kilograms. Keep that in mind. This TR exactly, Duncan, is going to be equal to mg, this big mg. If the system is at equilibrium, the tension that at this point, we call it tension R, right, is going to be exactly equal to this tension. And that tension is going to be exactly equal to mg, right? Since nothing is moving. If big M doesn't move, that means the T that pulls it up and mg, they're going to be exact. Okay, so we got this too. TR is going to be equal to mg. No, torque of TL is going to be equal to torque of TR. Torque of TL is going to be equal to torque of TR. Torque of TL is how much? It's going to be TL multiplied by what? Exactly the magnitude of the R from the magnitude of the R to the center, which is this. How much is it? 20 centimeters. 20 centimeters. You can convert it to meters, but I'm not going to convert it to meters because everything is in centimeters. They're going to cancel out. The units are going to cancel out. And torque of TR is going to be what? TR multiplied by 30 centimeters. You see, guys, if you converted it to meters, well, you would exactly get the same result. Then TL would be mg sine theta 5.0 9.81 sine of 30 degrees multiplied by 20 equals to TR is going to be m 9.81 30. The 9.81s, they're going to cancel out, and you will find out that's it. Make sense, guys? Questions? Any question I can answer? Are we all good? So I'm gonna stop recording, guys, and I will convert this into MP4 and I will upload it on YouTube. Once the link is ready, I will post it on Canvas. I'll let you guys know either with an announcement or an email when it's done.